Good day and welcome back for the fourth part of our discussion on inverse functions. In our previous video, we introduced a formula for differentiating an inverse function at a point A. And to begin with a reminder, the formula for f inverse prime of A, assuming some hypotheses are satisfied, is 1 over f prime f inverse of A. So in order to calculate this derivative, we need to determine two things. We need to determine the value, f inverse of A, and then we need to evaluate the derivative, f prime, at that number. We finished our previous discussion by investigating such an example, and now is the perfect time for you all to practice an example. And if we were meeting, in person this semester, this is where I'd be turning the floor over to you. I would ask that you spend somewhere between, 4 to 7 minutes and see if you can find f inverse prime of 2 for the given function. And let me once again remind you, I'm going to frequently ask you to pause the video and work through something. And I know it's probably really tempting to just wait for me to start talking again, but you will take out of this experience what you put into it. And mathematics in particular is something that you learn by doing. So pause the video, see if you can determine this derivative. So hopefully you've paused the video and thought about this for a few minutes. F inverse prime at 2, we can rewrite this as 1 over f prime f inverse of 2. And we immediately see those two quantities we need to solve for. What is the number, f inverse of 2, and what is the derivative, f prime? And the order you find these things is really irrelevant. So if I want to know what number is f inverse 2, well, by definition of the inverse, it is going to be the input to the function f that gives you out 2. So can we determine a value when substituted in for x, we get back 2? And I realize that it can be difficult to look at this and just think about what value of x would satisfy the equation, but we really need to try to make it as intuitive as possible. The square root makes it look more difficult. So essentially we're asking, what is a value of x that makes the quantity under the square root equal to 4? And note we're adding together 4 quantities. If they all happen to be 1, they would add up to 4, which happens precisely when x is equal to 1. So because f of 1 is equal to 2, f inverse of 2 is equal to 1. So that's the first kind of piece we need for our puzzle. Now we need to know what is f prime. And looking at the function f, it's a composition, which means we're going to need the chain rule, which we discussed in our previous example. So in this case, f prime x is going to be the derivative of the outside function, which is the square root. So 1 over 2 square roots. We evaluate that at the inside function, x cubed plus x squared plus x plus 1. And then we multiply it by the derivative of the inside function, 3x squared plus 2x plus 1. And hopefully as you go through and practice more and more examples, calculating these derivatives will, just like they were in Calculus 1, become quicker and more efficient. Now we need to know the specific value f prime 1. Let's go ahead and just continue on and do that computation to the side. So f prime of 1, so we have a fraction, the numerator would be 3 times 1 squared plus 2 times 1 plus 1. In the denominator, if each x is a 1, we'll have 2 times the square root of 1 cubed plus 1 squared plus 1 plus 1. So that would be 6 over 2 square roots of 4. And if we do some quick simplification, 6 is 3 times 2, so we cancel off the 2 on the bottom, and the square root of 4 is 2. So the derivative we are looking for is 1 over 3/2, which is 2/3. And I'm going to circle my solution just to make it as easy as possible for the reader to find. And once again, let me just note that this is more or less kind of what your work should look like when you solve these types of problems on homework assignments or exams. Let me go ahead and ask a secondary question related to the interpretation of the derivative. Let's use this information to find the equation of the tangent line to this curve y equals f inverse x at x equals 2. And note, in order to find the equation of this tangent line, you do not need a formula for f inverse of x. I would strongly encourage you not to try to find a formula for f inverse of x. Algebraically, that's something I'm not sure we can possibly do. But in order to have the equation of this tangent line, remember its generic form. It's going to be the slope of the tangent line, which is the derivative at 2, and it passes through the point given by 2 comma f inverse of 2, because f inverse is our function of interest. And we don't have to think too hard about either one of these values. F inverse of prime of 2 is the number 2/3 that we just found, and f inverse of 2 is this quantity 1 we determined as part of our work to the previous problem. So the tangent line is y equals 2/3 x minus 2 plus 1. So almost an afterthought once we've done all of the work required to answer that original problem. At this point, we've completed the material associated with this first section we're covering, but I always find this to be a good opportunity to review a few derivative and antiderivative examples from Calculus 1. Because before we know it, we are going to be introducing all kinds of new integration differentiation formulas, and we'll want to make sure that we are quick and efficient with the basic properties that we already should be familiar with. So for example, if I would like to differentiate secant of 1 over x, what rule of differentiation do we need? The chain rule. It's a composition. So the chain rule tells us we differentiate the outside function. The derivative of secant is secant tangent. We evaluate that at the inside function, that is 1 over x. And then by the chain rule, we multiply by the derivative of that inside function. And just as a reminder, 1 over x is something we've probably differentiated many times. And the most convenient way to do so, if you've forgotten the formula, is to use the power rule. 1 over x is really x to the minus 1. The power rule tells you that power minus 1 comes down front, and the new power is 1 less. So minus 1 is minus 2, which is maybe more conveniently written as minus 1 over x squared. So the derivative of secant of 1 over x is secant 1 over x tangent 1 over x multiplied by minus 1 over x squared. And you should make sure that you are familiar with the standard rules of differentiation, things like the quotient rule, product rule, chain rule, power rule, along with all of those common differentiation formulas that we've encountered. Moving on to an example involving integration. If we are asked to antidifferentiate the function x over the square root of 2 plus x squared, when it comes to integration in Calculus 1, you are actually, believe it or not, in an ideal scenario. You have essentially two approaches. You can either directly or through algebraic manipulation compare to your formula of common indefinite integrals, or you will need to use substitution. In this case, you will most definitely need a substitution. But note, you have this quantity underneath the square root, 2 plus x squared, and up to a constant, its derivative appears outside of that function. So this is the ideal scenario for a substitution. And typically our first choice for u is to try the largest possible inside function. So in this case, it would be 2 plus x squared. Then du would be the derivative of that quantity, 2x dx. And what we need to do with a substitution is take this original integral, only involving x, and rewrite it in terms of an integral only involving u. And x dx can be conveniently rewritten as 1/2 du. So note, 1/2 is a constant which can be pulled out front, and we're left integrating 1 over the square root of u. And just to reiterate, there's no middle ground. All x to all u. And remember, the substitution does not solve the integral for us. What it does is allows us to rewrite in terms of what is hopefully a simpler and easier to evaluate integral, which it is. 1 over the square root of u is u to the minus 1/2. And recall, this is a common formula. If we would like to anti-differentiate x to the n, as long as we stipulate n is not equal to minus 1, we would have 1 over n plus 1 x to the n plus 1 plus c. In our case, we have n equals minus 1/2. So we have the 1/2 hanging around out front, and then we have our antiderivative. Minus 1/2 plus 1 is 1/2, and we put a plus c. So we have a 1/2 over 1/2, which cancels. And recall, when we are using a substitution to solve an indefinite integral, our last step is to always resubstitute. The original question was phrased in terms of the variable x, so our solution should be given in terms of that variable x. So we make each u a 2 plus x squared. So we're left with 2 plus x squared to the 1/2 plus c, which is perfectly fine, but you could also write that as the square root of 2 plus x squared plus c. And once again, to just kind of focus in on the presentation of the work and the notation, we write our integral symbols and our differentials at each step until we are done integrating. Because it's an indefinite integral, we include a plus c, and we line things up in a vertical column, and we write our equal sign at each step. And at this point, if you turn to the next page in the note packet, you will see 2 more antiderivatives. What I would like you to do is, before viewing the next video, complete those antiderivatives on your own. Once you have done so, then go ahead and view the video where we will discuss the details. So stay tuned. Take care.